don't have, if the first 2 weeks you don't run them
pull up the calculus.
It's not a third order differential equation.
There are no
rounds whatsoever.
and I show them the annual approximation.
So I don't have to stand back and work on.
Julian! Hey! How are you? Good to see you.
Good to see you too. So you changed the office, right?
I changed office.
I see. So I think I see. I'm glad you just look fully green now.
You can sign me.
But I couldn't believe
I'm at the Angela Hall now.
Would which
Sit down.
Like one of the early manned space flights, Gemini has one of those things, they have these onboard computers. One flight. Astronauts do it. Not too hard.
Yeah, thank you. Couldn't quite get it. Except I'm gonna eat my, I gotta eat when I'm gonna eat my lunch.
Okay, I think we can make a start. It's about time, yes? Okay. Yep. All right, let's start. Hi, everybody. I'm Hannah Rana. I'm a postdoc here at the CFA, and I work with Jenna. And I'll be introducing Jenna today. So, as an astrophysicist at the Center for Astrophysics, Harvard and Smithsonian, Jenna Samra develops remote sensing instruments to observe the solar corona and the Earth's atmosphere. She leads the CFA's high-altitude infrared coronal instrumentation program, the subject of today's talk. Jenna has also contributed to ECHO, a set of EUV imagers and spectrographs recently proposed as a NASA Small Explorer, its predecessor Kool-Aid, which will collect spectroscopic data during the high-sea flare rocket flight, and Methane Air, which makes airborne measurements of atmospheric methane and is a pathfinder for methane SAT. Before joining the CFA as a graduate student in 2014, Jenna worked at MIT Lincoln Laboratory on the development of environmental monitoring sensors. Jenna obtained BS and MS degrees in electrical engineering from Penn State in 2006 and 2008, and received a PhD in applied physics from Harvard University in 2018. Very excited for your talk, Jenna, and also it's been raining the last few days. Seems like you've brought the sunshine with you. So without further delay, over to you.
Thanks so much, Hannah. I'll assume the mic is working unless I hear otherwise. So thanks, Hannah, for suggesting me for a speaker, and for to the organizers for giving me this spot. So those of you who might have seen a talk that I gave 3 years ago, this first slide might look very familiar. This is going to be an update on a colloquium I gave in 2020 on the same program, but we've come a long way since then, not only on our upcoming missions, which both have flights next year, but also analyzing the data from our previous Eclipse missions. So I'm excited to tell you about that. So maybe this doesn't work. Yes, it does. Okay, so I'm going to start with some background on the solar corona, its magnetic field, which is behind all of the instrumentation that we're building here. I'm going to talk about how we could measure the coronal magnetic field using polarimetry in a making remote sensing measurements. And I'm going to talk about the IR coronal emission lines that we make the polarimetric measurements of, which are in themselves useful as diagnostics of the coronal plasma. Then I'm going to talk about our magnetometry pathfinder. I've given parts of this talk before, so I'm going to gloss quickly over the instrument, but I'll show you some of the newer science results in a paper that just came out this year. And I'll talk about the upgrade that we made to the airspec pointing system, which sadly didn't get an Eclipse flight, but it did succeed in its test flights in 2021. And then the most exciting part of this talk, I'm planning to spend hopefully about half the talk on our instrumentation that's currently under development to get people kind of excited for what's coming next year. We have 2 missions that have flights in 2024, an Eclipse mission in the April 8th, 2024 eclipse, and then a high altitude balloon mission in September 2024. All right, so in my group studies the solar corona. I'm part of SSXG here. So I'm going to start with some background on the corona. Here we see a beautiful picture of the corona during the 2020 eclipse. And I wanted to point out a couple of features. So we see these loop-like features in much of the corona. We see these extended streamer features. We see that the corona is very large. It's very extended compared to the solar disk itself. And this gives us a hint that it's not in equilibrium. And in fact, if we look at a video from a European satellite of the corona, we see just how dynamic it is. And we can see all these features kind of moving as the sun rotates and changing. And in fact, the activity here can sometimes be even eruptive, right, as we know. So here are solar flares, an example of a solar flare, energy released as light, a coronal mass ejection, which is plasma and magnetic field and particles propelled off from the sun. And then here we see a filament eruption, and then some coronal rain after a flare, kind of these coronal loops being illuminated as plasma flows back down. And so it turns out that all of these features of the corona, so its extended non-equilibrium nature and the loops and the streamers and the eruptions, they're all related to the coronal magnetic field. So the coronal magnetic field, so first of all, the corona is very hot. It's not in equilibrium. We understand that the magnetic field stores the energy to heat it. We don't exactly understand how that energy is converted from ordered magnetic energy to heat. But the magnetic field also defines the structure and the dynamics of the corona. So the structure you can see here, here's a magnetic field model, and here's an eclipse, a processed eclipse image with these processed to bring out these very sharp magnetic field lines. You can see that the plasma is actually just following right along the field lines, and then the free electrons in this plasma are what is producing this white light eclipse image. They're scattering light from the underlying photosphere. So the magnetic field also stores the energy for those eruptive events that we saw in the previous slide, the flares and the coronal mass ejections. When the magnetic field gets into an unstable energy configuration, it reconnects into a more stable configuration, and that extra energy is released either as light in the flare. It propels, the material from the corona in the coronal mass ejection. And so, obviously, the magnetic field in the corona is really, really important to understanding the corona. But it's really, really challenging to measure, and that's where our instrumentation program comes in. So it's very weak. The fields in the corona are much weaker than those in the photosphere. You can imagine them maybe on the order of, a few Gauss up to 10 or tens of Gauss in the strongest regions. And one of the ways that we can measure coronal magnetic field, the way that I'm going to talk about today, is by using looking at emission lines. So these are lines that are emitted by the corona, by ions in the corona, highly ionized iron, silicon, sulfur, etc. And these lines, if you measure their polarization state, they can give you the line of sight magnetic field strength, so the field strength along the line of sight. They can give you the plane of sky field azimuth. And so this is kind of one of the best options for making magnetic field measurements remotely. But it's really challenging. So UCOMP, which is an instrument out at NCAR, managed by NCAR High Altitude Observatory and out on Mauna Loa in Hawaii, it can routinely measure magnetic azimuth, as I mentioned, and as I'll show in the next slide. But the field strength measurements are really, really challenging. They've been demonstrated just a few times, and this is what we're going after with one of our instruments, is a field strength measurement. And of course, DKIST, the Daniel K. Inouye Solar Telescope, which is now online, I think maybe still in commissioning, but also making some science observations in Hawaii, on Haleakala in Maui, will measure the line of sight magnetic field strength. And DKIST has a very high resolution, a large 4-meter aperture, and a relatively small field of view. And so our instrumentation program is actually going to make complementary observations, and they are complementary in these ways. They're high altitude, so we have reduced atmospheric scattering and absorption compared to DKIST. So better seeing, essentially no seeing, as well as reduced scattering and then reduced atmospheric absorption, which is important for the infrared. I'll talk about why we're in the infrared in a little while. We have a large field of view, so we're going to be viewing the global corona as opposed to the small pointed field of view of DKIST. And our plan is to ultimately make continuous long duration measurements of the coronal magnetic field. So to actually observe from space or from near space, where we have no day-night cycles, and we can observe the corona over at least one or many solar rotations. Okay, so how does coronal polarimetry work? How do we actually get the magnetic field out of these emission lines? Well, I mentioned that we need to measure the full Stokes polarization state. So the kind of measurement in the absence of noise that we would make is shown here. So we have, here's the emission line that we would measure. Looks kind of Gaussian. Then we measure the linear polarization, which is these Q and U states. They're two orthogonal linear polarizations. They look like a scaled version of the intensity. And then the circular polarization is what allows us to measure the line of sight magnetic field. That looks like the first derivative of the intensity. And so it turns out through radiative transfer in the corona, in the optically thin corona, we have these relatively simple equations for how the line of sight field strength and the magnetic azimuth relate to the polarization vector, and they're just by these very simple equations. The trick here, and the reason it's so difficult, is because these polarization states are somewhere between 1 to 2 and in orders of magnitude lower than I in the case of linear polarization, and then like 3 to 5 orders of magnitude lower than I in the case of circular polarization. And that's why it's so challenging to make these measurements, because you have all the noise of your coronal line, and you're trying to pull out this very small, all the photon noise from your coronal line and the continuum beneath it, and you're trying to pull out this very small signal from that noisy data. And you also have more systematic issues when you actually go to build a polarimeter like crosstalk, which I won't get into too much. But if you can actually manage to measure these, you might, and you had no noise, you might see something like this, which is some model data courtesy of one of our co-Is, our Corsair co-Is, Maxim Kramer. So at each pixel in the corona, you actually get one of these profiles, and you can see that in the regions of high magnetic field, these active regions here, we see some strong linear polarization signal, which then can be immediately translated into an actual line of sight field strength. And then likewise, Q and U can give us a linear, the linear polarization can give us the azimuth, the plane of sky azimuth. And I'll show some examples of that in the next slide. So here's examples from two instruments. The one on the left is the linear is an example of what the linear polarization gives you. Now this is an example of the COMP instrument, which was UCOMP's predecessor. Again, COMP is Steve Tomczak and Enrico Landi's instrument from NCAR High Altitude Observatory. And here we see how a measurement, about a 1 hour measurement of the linear polarization can actually give you the azimuth in the plane of the sky here, as denoted by these vectors. And actually, so here's the actual linear polarization. Here are the derived vectors. And then the deviation from a radial azimuth, you can see kind of immediately follows these AIA images of plasma, but this plasma, of course, is following magnetic field lines. So you can see the same kind of structures here. So this is a 1 hour measurement, and it's a really nice measurement of magnetic azimuth, and COMP makes these measurements, and one of our instruments is going to make these measurements, as I'll talk about. The much more challenging measurement that hasn't been reproduced since 2004, at least hasn't been published, is the measurement of magnetic field strength. And so this is a measurement from Hao-Sheng Lin that he made with the Solar Sea Telescope in also on Haleakala, and a spectrometer called OPHIS that he built. And so you can see, this is, again, a 1 hour, about a 70-minute exposure. It's a bigger diameter than COMP, and it's a bigger pixel. And you can see kind of the linear polarization signal here in the Gaussian, and a very weak circular polarization signal, almost, kind of in the noise, more or less, for these different observations. And so this is the challenge. This is what's so difficult. And this is why these measurements until now have not been made routinely. And so we ultimately want to make these measurements routinely, the line of sight field strength measurements, and then those are going to allow us to better constrain magnetic models. We'll always need models, and hopefully eventually better understand the magnetic field of the corona if we make these routinely. Okay, so what are the lines? So we've seen a lot of emission line profiles. What are the lines that we're using here? So we are using lines in the infrared. The reason, at least the group at CFA is focusing on the infrared. The visible lines can also be useful. Visible and infrared are more useful because the longer wavelengths give you a larger ratio of Zeeman splitting it goes as lambda squared. And so you end up with a more sensitive measurement of the magnetic field for the same field strength. And so we're focused on the infrared, partly because it's challenging, and so it has not been as well characterized. So here are some of the key lines in the infrared. Here are the different instruments that I'm going to talk about today. Our AirSpec Eclipse instrument, which flew twice. It measured most of these lines, all but two. These two lines are here because they're really important for other instruments, especially the ground-based ones. They have a nice atmospheric window region at 1 micron. And then our balloon instrument is going to focus on this 4 micron line, which I'll talk about on the next slide. And then our Eclipse instrument is going to actually measure all these lines and more. And so from these lines, even if you don't measure polarization, you can get plasma temperature, density, and line of sight velocity. Also plane of sky velocity if you can track just by tracking motion through the image. And if we measure the polarization, we can get the magnetic field. So here's an example of just a group in Hawaii, Shadia Habal and Ben Bo's group, measured two different ions at different temperatures and different visible wavelengths. And you can see how the different temperatures pull out different structures in the corona. And then this is a prediction that Phil Judge of NCAR HAO made in 1998 of the lines in this passband and their predicted field strengths. These are the lines that are highlighted. But this is a passband that's been of interest for a long time. It's been some of it can't be accessed from the ground, and so it's been challenging to explore, and that's one of the places where our instrumentation program comes in. But I want to stop and just talk about this line because it's an important one. This silicon 9 line at 3.9 microns. This line is special because it has a very long wavelength. Typically, when you have a line at longer wavelength, its intensity would be lower because both of the excitation processes, the radiative excitation and the collisional excitation, become less likely for various reasons at longer wavelength. So it's relatively bright for where it is in the spectrum, and it's long wavelength. So it has much stronger Zeeman sensitivity, lambda squared, compared to the iron, let's say the commonly used iron 1 micron line. Now, and this is kind of captured in these plots that were originally produced by Phil Judge and then reproduced by Tom Shad in a DKIST workshop, basically showing a sort of a metric. The circle here is a metric of how useful we think these lines will be, and you can see. And then there's just wavelength versus temperature here. We can see that there's this hot line over here, which everybody already knows is really useful, and people are measuring it. UComp is measuring it, and DKIST is measuring it already, and the Indian mission Aditya is measuring this. But this line has been measured only pretty seldom. It is a DKIST target line, and it's nice because it gives you complementary temperatures. It's a much cooler line. And it looks like it's just going to be just as useful for measuring that line of sight magnetic field, which is up here, and then also the magnetic azimuth down here. And these are the DKIST measurements that just came out of this line. This is a very small, DKIST has a very small pixel. It has a very small slit, and the cross-track pixel is about 1/10 of an arc second. It has the large diameter, and in a 200-second exposure, they can pull out a spectrum that looks like this. And you can see that the problem is there's a whole lot of telluric absorption for DKIST. So they have to pull the line out of the atmospheric spectrum, and they do that, and then they get like a nice profile of this line in a 200-second exposure. And so what we want to determine is, one of the things we want to determine is would high altitude measurements of this line be helpful? Would it be even more useful to be able to go above the atmosphere and not only not have the extra noise from the reduced transmission, but also not to have to deal with as much of this background spectrum? And then, of course, DKIST is measuring over at very high resolution over a small field of view, so our measurements over a larger field of view, lower resolution, will be complementary. So this brings me to our what we're going to contribute. So this is our CFA's high altitude instrumentation program, the timeline. We started in 2017 with our airborne eclipse spectrometer, airborne infrared spectrometer, which was an eclipse spectrometer. We upgraded that instrument and flew it again in 2019. We got even better data, and I'm going to show you a little bit of our results in this talk. We then upgraded the pointing system, and we were hoping to feed a new focal plane instrument and the old AirSpec instrument in an eclipse flight with that new pointing system. But unfortunately, we got canceled by the pandemic twice, so we ended up just doing a demonstration flight on the solar photosphere in 2021. And then now we have the future instruments. So we have 2 flights coming up in 2024. We have our next eclipse instrument, which takes a feed from this pointing system. And we have our balloon instrument, which is going to target that 4-micron line from above the atmosphere and hopefully actually make magnetic field measurements. Most of these instruments do not. And then finally, so we're going to do a 1-day test flight of our balloon instrument in 2024, but in 2028, we want to actually launch that instrument from Antarctica. We want to get into the polar vortex, circle the pole. We'll have no day-night cycles in the southern summer, and we will actually be able to measure for a whole solar rotation. We can stay aloft for at least a month or so, NASA has told us. And so we can actually measure the magnetic field as the corona rotates and make 24/7 continuous measurements over the global corona. So that's really exciting. All right, so I'm going to go pretty quickly through AirSpec and its results, and then on to the upcoming missions. But AirSpec was a grading spectrometer that flew on the NSF Gulfstream 5. It's on this optical bench here, mounted in the plane. You can see the window. It comes in through a relatively small window. The light comes in, enters a telescope, and then into a spectrometer, which is all shown here. The spectrometer is a slit spectrometer. The light is folded up in kind of an interesting way in order to put our 6 target lines on the detector. So we're using actually 2 orders of the grading, and we're using the top and bottom of the detector differently. And that was so that we could cover this wide 1.4 to 4 micron range at relatively high spectral resolution. And so, of course, AirSpec uses a diffraction grating in order to disperse the light. So it's a grading instrument. Because we're on the Gulfstream, we have to fly on an isolated optical bench. We have to have active image stabilization, which I'll talk about a little bit more later. And then we have to be able to move the bench back and forth because we're looking through this little window. And as the sun angle changes, the position of the sun changes, and we need to keep it on this mirror. And AirSpec did not measure polarization, so it couldn't measure the magnetic field. But what we were trying to do was open up this spectrum, this 1 to 4 micron spectrum, 1.4 to 4 micron spectrum, which had been mostly unexplored up until now, and actually kind of characterize the lines inside that passband to see which ones would be useful. So this is the platform it flies on, and this is the platform that we flew on again with AirSpec, and we will again fly with ACES. This is the NSF Gulfstream 5. It's operated by the National Center for Atmospheric Research. It flies at about 50,000 feet. That's its ceiling. We usually fly 45 to 47. it can fly at about 600 miles an hour, but which means it can't keep up with an eclipse, but it can give you about 50% more time in totality. And then we have these, you end up looking through a pretty small viewport, like here's that same window mounted in a different viewport for a different eclipse geometry. And you end up, also, depending on where you have to go, flying liquid nitrogen on board. So here's our LN2 tank, which we needed in the 2019 flight. And because you're trying to mount everything on this airplane, you need to make sure your system is modular. So we have a system that the optical benches break apart, and then they're pinned and they go back together in the exact same position once we get on the airplane. So these are the 2 eclipses we observed with AirSpec. We observed the 2017 US eclipse over Kentucky. We were based in Chattanooga, Tennessee. In 2019, we observed the eclipse just north of Easter Island, and we were based in Peru. So we had this long ferry, 6 hours to get out to the observation point, and that's when we needed the liquid nitrogen, because we had to keep the instrument cold through that whole flight. We landed to refuel on Rapa Nui, Easter Island, and got to spend a day there, which was really neat. And so this is where we pointed. This is the corona at the time of the 2 air eclipse observations, as imaged by our by our context camera, which wasn't the best imager, but it did the job of giving us context. So that's why these images aren't the prettiest. But we pointed our slit to different positions in the corona, mostly focusing on the east and west limb, where we expected the brightest emission, and that's because both of these eclipses happened on the way or at solar minimums, so the corona wasn't too active, and this was kind of our best bet for seeing these emission lines. We also had some coordination with the extreme ultraviolet imaging spectrometer at the limbs here. This spectrometer is a spaceborne spectrometer on board Hinode, and it measures extreme ultraviolet emission lines, but some of the same ions. So we can do some interesting temperature and density comparisons with ice. We got really long duration in the 2019 eclipse because we had a tailwind. It was a long eclipse, and we were in the airplane, so it was really nice. So this is what our spectra look like. I've shown a lot of spectra before, so I'm just going to show one slide. This is actually a spectrum that included some of the chromosphere. It was right at the end of the eclipse, so there's actually a lot of hydrogen and helium in here, which I haven't labeled, like these unlabeled lines. They're not coronal. They're cooler temperature lines. But you can see we actually measured, the lines in red had never been measured before. AirSpec made the first measurement of those. So the sulfur, the iron, the iron 9 line was actually measured in 17, and then the other 4 were measured in 19. And actually, these 3 weren't even target lines. We found them kind of after the fact. Actually, one of my reviewers found one of them in a paper I submitted, and so then we started taking a deeper look at the spectrum, and that's why I've shown this limb observation that includes the chromosphere, because that's where these lines are the brightest. They're really, really weak, very close to the AirSpec detection limit, but we did measure them, and we're in the process of publishing a paper on those 3. So you can see the lines here. You can see they have a variety of different temperatures. And the year in which they were measured. And then this pair of lines is special because it's a density-sensitive line pair, so we can actually use that pair of lines to check whether we can make reasonable density measurements using in the infrared. This is commonly done in the extreme ultraviolet. In the infrared, it's a little bit trickier because the lines are more photoexcited than they are in the extreme ultraviolet, and so you need to take that into account, and I'll show some results on that. I also want to highlight that in 2019, we measured this silicon 9 line. So this line this is the one that we're pretty excited about, that we're now building a whole mission around, and the one that I showed you that DKIST measured just recently, but had a lot of atmospheric absorption. So, our line profile is a lot cleaner. And the intensity level is similar, but you can kind of see visually, I don't have a direct comparison, that the noise is less. And that's because it's just because we have much bigger pixels. It's a very different instrument than DKIST. But again, for the global corona, for making that sensitive measurement of the magnetic field, and for not having the benefit of the 4-meter telescope, that's what you need. And so you can see we made a really, this was a very strong line for airspec. And so that was nice to see. And here's a couple of, an active region measurement of that line, and then a quiet sun measurement of that line, just the intensity as a function of distance from the center of the sun. So the line stays strong quite far out, which is also means that it could be a really nice diagnostic for the coronal magnetic field. And then the shaded region here is just kind of the uncertainty in our radiometric calibration, and the arrow bars here are the uncertainty on the actual line strength, just due to noise. So I guess I wanted to highlight this because we're gonna now build a whole mission around this line. Let's see. But before that, I'll talk a little bit about the science that AirSpec did. So one thing we can do is make these plots for a bunch of different lines and compare with models and see whether we're getting particularly the impact of photoexcitation correct in our coronal models. So these models are by Giulio Dazzana in the dashed and solid lines, and you can see that photoexcitation is important. You only get the fall off correctly if you've modeled photoexcitation, and that's because these IR lines have the underlying photosphere is relatively bright in the infrared still, and so these lines have contributions from that. And then I wanted to point out here that there's a pretty big difference between the east and the west limb. So one of these was a slip position on the west limb in 2019, and one was on the east limb. You can see that this hot sulfur 11 line is much stronger on the east limb, and then this cool iron 9 line is much stronger on the west limb. And so it turns out that, so this was not just an error in our calibrations, this was actually seen by other instruments, including AIA. If you just plot up a couple of AIA bands at similar temperatures to the AirSpec lines, you can see that this slit was just over this hot region, and this one was over a much cooler region, especially close to the limb where we had good signal. And it turned out that we were actually able to get quantitative temperature measurements using working with Giulio. This is a paper that just came out earlier this year where we actually measured the temperature of the corona using not only the AirSpec lines, but a few others from both AIA, the measurements here, and then the extreme ultraviolet imaging spectrometer on Hinode. And we got pretty consistent, fairly consistent measurements that did show a temperature difference between the two limbs. We also measured the density using that density-sensitive line pair that I talked about, the sulfur 11 line pair. And we compared with, we had other eclipse measurements out of the High Altitude Observatory. Paul Bryans and a team there actually had a polarized brightness detector that measured the the corona, and the polarized brightness will give you the electron density because it's the electrons, only the electrons, the scattering off of the electrons produces a polarized signal in white light. And so we compare that again with ice and with, well, here we've just compared with ice. So we see very good agreement between the densities on the east and west limb. The reason I've only compared with ice here is because this is an example of the density calculation that you make if you don't account for, don't remove the contribution from photoexcitation. So you have a contribution to the line strength from collisional excitation, which is a probe of the density, because the more dense the electrons, the more collisions. But then you also have this photoexcitation. And so here we used ice data that wasn't corrected for collisions, and we have AirSpec data that was not. And so we get good agreement. And then the pull cam data here was corrected for the line of sight. So the way that you do the correction is you, instead of just looking at the full line of sight integrated line strength, you try to pick out the line strength that's just coming from the plane of the sky. And here we see that, so we were able to adjust AirSpec for the line of sight contributions and pick out the region using a model that was just coming from the plane of the sky, and we see good agreement with the pole cam densities. And the reason So this basically not only gives you kind of a good check on the densities, but it tells you that the IR lines can be used to measure density, and and that we have a model that can reasonably well predict the apportionment along the line of sight where the line intensity is coming from, and so we can actually remove that effect, which is really important for the IR lines because they're photoexcited. Okay, so that's the results from AirSpec. So now I'm going to start talking about what we did after that and what we plan to do. So after AirSpec, we built this. We basically upgraded the AirSpec pointing system. AirSpec had a small mirror that did the pointing in 2017 and 2019. This mirror was a part of the context camera system, or the image stabilization system rather, included this small mirror and the AirSpec context camera. So what we wanted to do was decouple the image stabilization system from the focal plane instrument, number one, and we wanted to put a bigger mirror on there. Instead of this 4x6 small mirror that flew before, we now have this large 12-inch or 30-centimeter mirror. Because it was so much larger, it had to go onto this large, heavy gimbaled platform, so there was some question about whether it would be able to keep up with the turbulence in the plane. But we needed this aperture in order to have a larger feed telescope and to ever be able to essentially collect more light on the airplane. So this is the system that flew in 2021. We hope to fly an eclipse and use these two focal plane instruments, the old AirSpec and then a new narrowband camera, to measure the corona. So this was going to provide spatial images of some of the same lines that AirSpec measured. But again, we missed the eclipses. They were in hard to reach places, and the pandemic shut us down. But this part of the image stabilization system we still needed to test because it's going to fly again and feed future focal plane instruments, both eclipse and even atmospheric instruments. It's anything that tracks the sun or the moon. It can do, and it could potentially be adapted to use other targets. So I'll show you how that stabilization system performed. So that's the mirror that we used to track. So you can see it rotates in azimuth and elevation. And then if you look at actually what it gets you, so this is some images of the sun. In the beginning, that was if you didn't do anything to stabilize. This is if you stabilize feed forward, and this is if you use feedback from the image. So essentially what happens is if you don't stabilize on the airplane, because you're looking over a small field of view, you can't really point to any location on the sun. If you stabilize just using an open loop stabilization system as we did in 2017, and you're basically just using a gyroscope to predict where the airplane is moving and then send the mirror to compensate for that, it does pretty well. But you have basically a drift in there that you're not really pointed exactly where you want. You have some kind of fixed offset that drifts over time. And then if you add the closed loop stabilization, you can point precisely wherever you want on the corona, and it roughly stays there. And there's a little bit of jitter, but the jitter is kind of at the 6 arcsecond RMS level. So for the type of kind of low resolution instruments that we're building, this is totally sufficient. And here you can just see the difference between kind of no stabilization and stabilization. And these are on very different scales here. And so we did flights where we just tracked the sun for kind of like an hour, however long we could keep it in the instrument. And so I think this is about a half hour of exposures. And you can see that most of them fall below 6 arcseconds RMS. So that's great because in 2024 we're flying a new instrument. It needs to be very stable, but it has like an 8 arcsecond pixels, or maybe even larger now. So that image stabilization system is going to be just fine. The important thing for this new instrument is the throughput and the altitude, and I'll describe why. And so the solar feed from Aspire enables both of those. So this instrument is called ACES. It's the Airborne Coronal Emission Surveyor. It's an imaging Fourier transform spectrometer. and it's going to fly in the same Gulf Stream that AirSpec flew on. And this is a collaboration. SAO is building the instrument, CFA is building the instrument, and we have collaborators at the NCAR High Altitude Observatory and the National Science Observatory. Solar Observatory, excuse me. And so our plan is to observe, we've picked an observing location. It's over Texas, near Austin, not exactly. And we're basing in Tucson, Arizona, partly to get us well out of the way of the eclipse, because the traffic, both air and land traffic can be very bad on the day of the eclipse. But also to, it gives us a nice opportunity to do some outreach with the University of Arizona and Whipple Observatory and other labs that are affiliated with with Arizona. All right, so what's ACES going to do? So it's going to survey the whole 1 to 4 micron corona. So it doesn't measure magnetic field, just like AirSpec, but the difference is that AirSpec measured these very tiny, relatively small passbands around known lines. So we targeted those lines. And ACES is going to measure the whole 1 to 4 micron range. This is an example of the spectrum that we expect to see. I think this is in the absence of noise. But you can see there's still a lot of atmospheric absorption, even from 45,000 feet. But this is one of the things we want to understand. Which of these lines, are worth going after and which are not? And there's enough less absorption. There's enough window regions at 45,000 feet compared to the ground that we can do a much better job of characterizing these lines. So the way that the data that the instrument produces is basically a spectrum at a number of pixels along this slot. So it's not a slot or a slit spectrometer, but the data kind of acts like one. We'll also have white light context images that have the whole full field of view. So we are limited. This is a Fourier transform spectrometer, so there's a scanning mirror inside it. And so we need to keep our readout time of our detector fairly short, which is why we don't take the full field of view all the time. So it's an imaging Fourier transform spectrometer, but we restrict our field of view to a small slot to keep a fast readout. And then once in a while, we open up to get a context image. So what are we going to learn? So one of the the foremost question is just what is the most information-rich set of lines in this passband? And again, we're above the atmosphere mostly, so we can do a better job assessing that than people can from the ground. And then we're going to do a suite of measurements that build on what I just showed you from AirSpec. So we're going to measure plasma temperature and density with radial distance, prove that we have a lot of temperature and density sensitive line pairs in this passband. Now we get like 20 lines or something like that. So that's really exciting. So we can make many more of these measurements than just those that were demonstrated with AirSpec. And we want to again explore the ratio of radiative to collisional excitation. And then, which can also give you other information about the Friesen distance, where charge exchange stops in the corona, how far out. And so there's, as well as telling us that our models for all these different lines are correct. And then we want to understand, we can do make some measurements of elemental abundances in the corona. And we're going to coordinate with Hinode again. We're going to coordinate with DKIST, with UComp out of HAO, and then hopefully with Parker Solar Probe and Solar Orbiter. And Solar Orbiter, I think, is going to be in Quadrature at this time. So we're excited to get some coordinated observations there. So we're starting to plan this now. And this is what the instrument looks like. So it's a Fourier transform spectrometer. So essentially, it collects the spectrum. Instead of dispersing the light with a grating, and then you're limited by the number of pixels on your detector, you're collecting the spectrum in time, sort of. You're collecting a modulated intensity signal in time by moving one of these corner cubes relative to the other. So you split the light into two paths. You then recombine the two paths, and one path in general has a different path length difference. There's a path length difference between the two paths. And so what that means is that you actually get interference, and the phase shift of your interference, or the phase shift changes as a function of wavelength. And so what you get at the end, because you're looking at white light, is something that's called an interferogram that just looks like a modulated intensity signal. And then when you Fourier transform it, you end up with your spectrum. And so we have a condensing telescope here, an afocal telescope, which actually just just concentrates the light so that this doesn't have to be so large. And then we have our Fourier transform spectrometer actually in a vacuum chamber here. And so here's the telescope and the spectrometer on the bench. Again, we have our same translation stage set up, and then the Aspire mirror and image stabilization system feeding AirSpec. We've done some performance predictions. So this is a plot of the signal to noise ratio of the lines that we expect to see as a function of distance from sun center. And so you can see there's actually, so I think there are 18 to maybe 21 lines, depending on how good our models are, that we should expect to see at least in the low corona, which is exciting. Out at 2 solar radii, we expect 3 lines to be strong enough to still be seen. And so then we can measure the fall off kind of over this whole this whole distance. And then our spectral resolution is a bit weird because it's constant in wave number space, and in wavelength space it's different from line to line. So this is a measure of the blue line is the instrument broadening function, and then the black dots are a predicted measured profile here. So you can see that we're really well sampled, and we have very high resolution at 1 micron. Not so much at 4 microns, but still this is significantly better than our spec was. And this probably out here it's enough to do some line profile analysis. Okay, so we're starting to get ACES hardware in. We have a set of test flights in December, so we really need to get a system together very, very soon. And the hardware is coming. Our vacuum chamber is probably arriving as I speak. So we're entering the build phase. We had a really effective design phase enabled by the engineers in CDP. And while we were waiting, kind of the biggest risk item here is this moving modulating corner cube, which allows us to modulate the light to get the interferogram, which we then convert to a spectrum. So running this in the presence of vibration on the airplane is what we absolutely need to test in December. The rest of it can be tested from the ground or has been tested already on previous flights. And so we built a prototype of this in the lab. We collected a spectrum of a low resolution spectrum of a 635 nanometer laser line just to prove that it was working. We have we're developing and refining now the control system for this moving corner cube. It basically tips in the direction of the arrows here. And this is just showing that we are able to bring our vibrations down to a level that's acceptable. The question is whether we can do it reliably in the airplane. Okay, so then we're going to go beyond solar eclipses, also next year, and we're building an instrument called Corsair. And this is a coronagraph. We don't need an eclipse. We're making our own eclipse. And it's a multi-slit spectral polarimeter. So we're back to a grating-based instrument now. But this time, unlike AirSpec, we're measuring polarization. So we're going to actually measure the magnetic field using the Stokes vector and the transformations I showed you at the beginning of the talk. We're doing this from a high-altitude balloon, and this is a NASA mission. By the way, the previous missions were all funded by the National Science Foundation, including ACES, the one that's happening in 2024. Again, we're collaborating with the High Altitude Observatory. We're also collaborating with the University of Hawaii. And in about a year from right now, we're going to have a test flight in Fort Sumner, New Mexico. This is a prerequisite for the long-duration balloon flight that we eventually want to have. It's prerequisite from NASA's perspective, and it's also prerequisite from our perspective. We need to make sure our instrument works before we go to Antarctica and get the real science. So we're going to observe for one day. It has to be in September because that's when the winds turn around and the balloon can go up and come down relatively in the same spot and not get taken by the wind. In 2028, that's the earliest that we can do in our circumpolar flight, because NASA also has been impacted by the pandemic and has a backlog of flights, but it probably works out pretty well for us from an instrument design, an instrument development perspective. All right, so our goal in the test flight is a fairly modest one. We want to make a measurement of the line of sight magnetic field anywhere in the corona. We just want to demonstrate this with 5 Gauss uncertainty. And that's not going to let us do all the science that I mentioned up above, but it's going to demonstrate that we can do that with this instrument, and then it's going to kind of pave the way for the Antarctic flight. And then we actually, the purpose of this flight is to then determine what we need to do better to change for Antarctica. So our science questions for Corsair are, we have kind of a plasma investigation, actually in 2 and 4, and then a magnetic investigation in 1 and 3. So we want to understand the kind of the topology of the magnetic field and where field lines transition from closed to open. So closed field lines being closer to the corona, in the inner corona, and then open fields connecting out in the heliosphere. And we can look at this during an 8-hour test flight. We also want to look at active regions and hopefully at CMEs. And these can only be addressed in an Antarctic flight. Most likely we're not, although we'll probably see, I'm sure we'll see an active region in 2024. But these are really targets of opportunity that we're going to address during the test flight. But then we also want to look at, we want to try to measure waves and flows in the corona. So this is more of a plasma question. So we don't, we need our velocities, our velocity measurements from that line, but not necessarily the polarization measurements for this one. So we can address 2 of our large science questions in the 8-hour test flight. We can address the other 2 in the Antarctic flight. And we're going to coordinate during both flights. So with DKIST, of course, a natural coordination partner, and UCOMP, HAO's instrument. And in particular, these instruments are really important because we need plasma diagnostics like temperatures and densities. And we need to understand kind of how we're doing relative to other instruments that make a similar type of measurement. So DKIST is going to be able to measure the line of sight magnetic field strength. It's only a matter of time, although they haven't published that yet. That's one of their main goals. And then UCOMP can measure, as I showed you, the magnetic azimuth very well and makes regular measurements of that. And so, and then of course both can also measure temperature and density. And so Corsair has been descoped. We used to have more lines so that we could make these measurements ourselves. We decided to, in order for schedule and budget reasons, to just focus in on the most interesting line. And that line, and so now we're relying on coordinations for the plasma diagnostics, and also for temperature coverage. We have that cool line, and then we want to see the hotter lines in UCOMP and DKIST. So this is what the instrument looks like. So it's a 3-stage instrument. We have a coronagraph with just a singlet objective lens. The reason we just choose a singlet and we choose a lens is because we want to reduce the scattering as much as possible. So mirrors scatter more than lenses because it depends on the difference of how different the refractive index is from the medium, the refractive index of the medium. So we chose a calcium fluoride lens, which has nice scattering properties. You make it as smooth as possible and keep it as dust-free as possible. And you're above the atmosphere, so you don't have to worry about scattering from the atmosphere. You're at 100,000 feet. And so we focus the light onto an occulter. This is an internally occulted coronagraph. We dump most of the heat and then focus the rest of the light onto a knife edge occulter here, which blocks out the sun at about 0.05 solar radii from the limb. And then we go into a polarimeter. The polarimeter works based on a rotating wave plate. So we have a linear polarizer and a rotating wave plate. The rotating wave plate can actually, it rotates continuously and modulates the light, and then you can decode that modulated light pattern into Stokes, IQ, U, and V after it's analyzed by the linear polarizer. And then we go, the final stage is the spectrometer. This spectrometer is in a vacuum chamber. It's all cryogenic because we're measuring 4 microns. And so we have a multi-slit plate, and then, which I'll talk about a little bit more later, a double pass lens and the diffraction grating over here, reflective diffraction grating, sending light back to the detector after it passes through the lens once. Now the slit plate, having multiple slits allows you to actually measure a spatial dimension of the corona, both spatial dimensions of the corona, at the same time you measure the spectral dimension. The trick is that you need a really narrow bandpass filter in order that you don't have spectral spatial overlap. So it needs to be kind of just 10 times your line width or something like that, on that order. Otherwise, you end up kind of with a lot of overlap on your detector, bringing in a lot of noise especially. Those filters don't exist yet, and so for the test flight at 4 microns, they exist for some of the shorter wavelengths. And our collaborators in Hawaii, Haosheng Lin, our collaborator in University of Hawaii, is working on working with a company to develop one of these filters for 4 microns. But for right now, we are going to space out our slits a bit more and for the demonstration flight only, and then have a narrower filter. I mean, a wider filter. So I'm not going to go through all of these specs, but this is what our data is predicted to look like. So the slits aren't shown here. So this would be like the Antarctic mission once we take 100 slits or so and then, stack them back together so that you get rid of the gaps in between them. So you can see that in a 1-hour exposure of the Stokes V signal, we can get kind of better than 5 Gauss uncertainty line of sight magnetic field. And in 10 minutes, we can do the magnetic azimuth, and then in just 30 seconds or so for the line of sight velocity. And so we're really excited about this. This is kind of similar to what others have done, but we have the advantage of being above the atmosphere to reduce the scatter, and also of having a larger pixel so that we can improve the sensitivity. So this is a really fast timeline to reach flight. So we're currently we've released most of our drawings. We're starting to get the optics are being made. They're starting to come in. The mechanical subsystems structures to hold them are going to be are out for quote, or a lot of them, and are coming in kind of over the next let's say until March of or early next year. We have a CDR on Halloween, a pre-integration review with the balloon office in March. And so we're working on subsystem assembly kind of all from here until April, and then assemble the whole instrument and align the 3 stages together in the month before we ship. We delivered a Wallops in the end of June. Wallops is, I didn't mention this by the way, but our instrument is pointed at Sun Center very precisely by a group at Wallops who has built a gondola, the Arc Second pointer, that can point precisely at either Sun Center, or it can point precisely. They do nighttime astronomy missions as well. So we deliver there, we mount on the gondola, and then the gondola and Corsair together go to Fort Sumner, and we have a flight, not on the 2nd, because the sun, at noon the sun will be occulted by the balloon at the 2nd. So we have to fly after the 8th. But that's the rough timeline. So that's it. I wanted to, there's tons and tons of people who contributed to this, all the Corsair ACES and AirSpec instrument and science teams. And so these are just hopefully most of them. But thank you.
Thank you very much, Jenna, for that illuminating talk. Do we have any questions?
So you were saying that you, if your filter is too wide, you get this spectral spatial confusion. Can you use the deconfusion methods that have been developed for like Muse and Echo to unfold that if you need to?
That's a really good question. Ed asked the same thing. So the difference is that this is mostly, we have one line and a bunch of continuum. So it's a different kind of problem. They had multiple lines that were getting confused. So you had like kind of a bunch of delta functions. This would just be, if you had a narrow enough filter that your line didn't overlap, or right, like as long as your filter was, a wide enough slit spacing that your line itself didn't overlap, because that would be a real mess if the line overlapped. Then the problem is that you just bring up the background that much more. So it's not so much a deconfusion problem as an additional noise, just letting a lot of extra noise in there.
Any other questions?
This solar cycle is apparently a lot more active than people had expected, which is great for the eclipse, for seeing active regions and brightness. But it does mean that things will be changing quickly. How quick is your scan for the MDS?
Yeah, that's a good question. It's a 20-second, 25-ish second scan. So I guess depending on, that's probably slow enough or fast enough for some time scales and maybe not for others. Probably maybe fast enough for most. I'm not positive. The issue is more that the signal in one scan might be low enough that we would need to average multiple scans, and we have up to a 6-minute eclipse. So then at the 6-minute mark, it might be, it might restrict what science we can do with it, certainly. I think that for the goals of ACEs, we're really looking for kind of like longer time scale. We're looking for things that hopefully wouldn't change too quickly. First of all, just to survey the line space, the spectral region, what lines are there. If you end up averaging intensity, that's probably okay if something changed. Looking at temperature and density, hopefully it wouldn't rapidly change in 6 minutes. I guess if we caught a CME or something, that could be kind of destructive. But on the other hand, that's relatively unlikely. So I'm hoping, and then the abundances. So I hope that most of the goals for ACEs are immune to sort of that time scale of change, but it's possible that something happens. But on the other hand, if something really rapid happens during it might be bright if it's and then it might give us something really interesting to look at. So, yeah. Any other?
What is the field of view of the chronograph? This balloon ball
Yeah.
chronograph.
It is. It's about 1 degree across, so it goes out to about plus or minus 2 solar radii. So about 1 solar radius past the limb, in the yeah.
What's the radius of the occulting disk?
Oh, the occulting disk 1.05 solar radii.
1.05.
Yes.
Okay. So in the process of shipping the instrument from the laboratory to the launching field, how do you protect this or prevent the dust from eluting the instrument?
Great question. We're actually designing our objective to be removable and cleanable, and we're developing a cleaning procedure. Our friends at High Altitude Observatory have a lot of experience with this, so they're helping us develop it. But so we'll actually be able to remove the lens and wash it, or there's sort of a number of different procedures depending on how dirty it is, and then replace it, and kinematically it'll go back to the same spot. And that's needed because essentially anytime we expose it, even to do a ground test, even if we ship it and it's okay, the ground test is going to expose it to a lot of dust. So we need to have that.
Sometimes in the field, it's open field, dust is always, density is very high.
Yes.
It's very easy to pollute the dance or the other instrument?
Yes, I know we have that experience with the airplane as well. It's not as important there, but we're aware. And there is a door I didn't mention, but there's a door that is shut until we're pointed at the sun, partly to protect the instrument from seeing the full sun. The door will also shield the instrument from dust when it's on the ground. So we do have mechanisms in place.
Dust basically dust it's okay for the normal regular telescope.
Yeah.
It's disaster for the crow.
Yes, I know. I know. It keeps me up at night. Trust me. Yeah.
So where on the plane is the window or exposure, and is it open totally to the sky when it's exposing, or how does it?
So the window, there's actually a number of different portholes on the plane. So we pick where we pick which one based on the angle of the sun for the eclipse. And it's not open, it's a sealed pressurized cabin. So it's not like Sophia where I think that's actually open. We actually ride in the plane. So it's all pressurized. So there's a couple overhead, there's a couple at like 15 degrees off zenith. There's, of course, all the side ones that the passengers would sit and look out of. We can replace those. They're plastic, but we can replace them with our sapphire viewport. And they have special frames that are built to go in there, and then you get the sub aperture. So we have a bunch of different choices for window.
Any further questions about that? No? Okay, we do have a lot of time for more informal discussion with Jenna with some tea and snacks, but please join me in thanking Jenna for the talk.
One thing I wanted to flag is looking for monitoring. I didn't want to ask if